Okay, Bismillahirrahmanirrahim. Okay, we are in the process of giving some introduction to the discrete time system. Let me start the annotation. So in the last day, we have just talked about the signal, any arbitrary signal. From this, of course, you can get your discrete time signal, xn. Of course, you need to select your sampling frequency, and there are some conditions for choosing the sampling frequency to avoid the aliasing. Not necessarily the aliasing is always bad for the signal processing. Sometimes you can use the aliasing as well for the signal processing. Okay, probably we can talk about that in future classes. We have given some example how the period of the continuous time signal and the discrete time signals are can be varied from one another. We have also talked about for the continuous time signal, we have given the frequency as capital omega, where for the discrete one, the normalized frequency can be given as small omega. This is in radian. This is in radian per second, whereas this is the capital F is in a cycle per second. That means that is in hertz. On the other hand, the small f it's can be written as the sample per cycle. Cycle per sample. Okay, so that should be inverse, the cycle per sample. And physically, we'd like to understand what is small f, and we have given the example in the last class. Okay, so now today we'd like to talk about a few things in the frequency domain point of view. We have the frequency domain in the discrete time signals. So we have converted our signal, and we would like to plot it in our relative frequency. And let's say this is small f. So if you can remember this small f can be represented as f divided by fs. And if that is a spectrum of the sequence, the spectrum of frequency, then of course the f also have the spectrum of f value. Let me give this line, introduce this line as 0 as a reference, and we can proceed in the right direction as a positive and left direction as a negative. For example, we can start with an example. That means, let's say we have the f is equals to 100, and we want to sample it with 200 sample per second. So that means we are choosing some value arbitrarily, okay? And from there, we can find if this sampling frequency remains constant, only this frequency, that means f will changes, and for each and every f, you can find some value in the frequency domain. So let's think that we are only considering this frequency 100 hertz. This is in hertz. This is also in hertz. So that gives us 1/2. And let's say this is that value 1/2. Of course, there is a significance of this. Graphically, what does it mean? If I have some signal like this, I choose a cos signal. for some reason. What does it mean physically? 1 divided by 2. Small f is equals to 1 divided by 2. What does it mean physically? From the last class. 2 samples per cycle. So where is the full cycle? So let's say this is the full cycle. So within full cycle, we have 2 samples. Those are the 2 samples. For the other cycle, we have again 2 samples. For the other cycles, we have other samples. So we may have this kind of scenario. What is the scenario? We have this sample, we have this sample, so on and so forth. Now, if we consider that, okay, at the end of the discretization of the signal, we only have these points. We have only those black dots. We don't have anything else. So in Xn, we have only those dots. Now, if we want to recapture our analog signal, that means xt, let's say xt hat, because that is not the exact xt, just we are considering that we want to capture the frequency, not we are not considering the amplitude. What I am talking about in case of Xn, let's say the actual frequency, analog frequency was f, and now for x hat t, we want to find what is the frequency. That means we want to get back the original frequency. Our target to find the value f, and it depends on the number of samples, of course. So whenever we have these dots only, these samples, and we pass it through a low pass filter, then we got back our analog signal, which was the mother signal xt, and where the analog frequency was this capital F. Eventually, for the discrete signal, the frequency was small f, and when we pass this analog signal, the Xn passing through an low pass filter, then we'll find xt hat. So if I consider the whole strain, it will be like this. Xt, you are giving it to the analog to digital converter. So from the analog to digital converter, you got this Xn. Here you have given the value of Fs. The criteria of xt was the analog frequency was f. The frequency, discrete frequency or relative frequency, f is equals to f divided by fs. It is known to you. Now, to get back the original signal, what we have done, we have given a low pass filter. Of course, you need to select the band of that low pass filter, where is the cutoff and other things. Okay, we'll talk about this later on whenever we'll talk about the filter design. So after that, you got this xt hat, where the analog frequency you got exactly f. In which condition you got the same frequency, Here is the condition. So in this case, that means we have f is equals to half. In that case, what we are getting here, the analog filter will give this kind of signal. So they have those samples, and linearly they might add those points, and the signal looks like this. So the green lines shows the analog signal output. From this analog signal output, you can understand that, okay, it actually still carry the same frequency. So we are happy. We are happy with this number. Okay, so it carries the same value. Okay, fine. However, it might have some problem if we change this sampling frequency. This sampling frequency, if we change it, then it might have the problem. Let me introduce that with some example. Okay. Let me erase this part and draw the things again. Okay. During this session, if you have any question, please raise your hand so that I can respond to your question. So let's start with the signal. Try to understand this very clearly. And if I have this scenario, let's say I have this let's have, okay, I need to redraw this thing for the clarification. Okay, let's do like this. Okay, I need to redraw part of it. Say cycle 1, 2, and 3. Okay, let's say three cycles have. So this is starting sample. It might have the second sample here. It might have third sample here. So we have sampled our analog signal. So let me give the name. Like this is our original signal F1, and we have sampled it with the sampling frequency Fs. Fs, where Fs is what? Let's say this is the time period of 3 seconds. 3 seconds. So what is the frequency of F1? Any of you? What is the frequency of F1? In 3 seconds, you have 3 cycles, isn't it? 1, 2, and 3. What is the value of F1 then?
1/3.
1 hertz, yes. Okay, you have 1 hertz. So try to understand each and every part physical instance with a physical instance. Now, what is the frequency of Fs? We have this sample, and this sample. What is the value of Fs in that case? In 3 seconds, you have how many samples you have? Can you find the value of Fs?
3.
Yes.
3 samples, sir.
Sorry?
3 sample. Fs 3 samples.
2 samples per cycle.
I'm asking about what is the value of Fs, capital Fs. That is the sampling frequency. That should be in hertz, isn't it? So whenever we are talking like Fs is equals to 100 hertz, what does it mean? In 1 second, you have 100 sample. That actually means, isn't it? In 1 second, you have 100 samples. So here, in 3 seconds, we have only, in the 3 seconds, we have 2 samples, not 3 samples, because these samples actually belongs to the next cycle. So basically, in 3 seconds, we have 2 samples. So in 1 second, we have 2 divided by 3 samples. and that is the value, that is the value of 2 by 3 is the value. This is hertz. So that is the hertz. 2 by 3 is the value for the Fs. I believe you can understand that. Per second, how many samples you have? Okay, so that is the value of Fs we got. Now we'd like to find the small f. What is the value of small f? So you can find it definitely by F1 divided by Fs, where F1 is equals to 1 hertz, and this is equals to 2 by 3. So you can find this is 3 by 2. So small f is equals to 3 by 2. This is of course more than half, that is 1.5. 3 by 2 means 1.5. So that is more than half. So let's say, okay, this is 1, and that is more than, so this is the point of 3 by 2. Okay, so that is the value of f. Now if you have this value 3 by 2, what will happen? What kind of analog frequency you will find after having the discretization? If you found this kind of samples, ultimately your signal looks like this. The signal looks like this. So you start with this F1, which is 1 hertz, but you end up with this frequency F1, let's say hat. Can you tell me what is the frequency of F1 hat? Can you find the frequency of F1 hat? What is the frequency? In 3 seconds, you have 1 cycle. So in 1 second, you have 1 by 3 cycles. So that is the hertz of the F1 hat. So the new frequency looks like 1 by 3, or you can say 0.33 hertz. Of course, by the diagram, you can find that the frequency definitely reduced. The red lines gives a higher frequency, which is 1 hertz, and the green line gives a very low frequency, 1/3 of that, and which is 1/3 of that, 1/3 of 1 hertz, that is 0.33 hertz. So this is a practical example of the alias signal. You will start with F1, 1 hertz, but you come up with the frequency 1 by 3 just because of low sampling value. Now, if you have higher sampling rate, as we have given in the last example, for example, we have this sample, this sample, this sample, like this, of course, your frequency will be preserved. Though the magnitude, the amplitude will be differ, but you can preserve your original frequency. In case of the black line, we have these samples, and we have given that for f is equals to half, you can preserve this. Okay, you can preserve this. So practically, it can be shown that if the value of f, small f, is more than half, in that case, you can preserve the frequency. You can preserve the frequency. So if I just illustrate these things in the frequency domain, relative frequency domain, this half has a very significant meaning of the relative frequency. If your signal frequency has a band of signal, let's say from 0 to 100, you need to sample it at least with 200 hertz. So this is in hertz. Your sampling frequency, the minimum, it should be 200 hertz to restrict the response between 0 to half. If it is more than half for any means, then it actually folded back as it has been done in the last case. So let me draw it. This is 1 and this is 3/2. If your signal goes like this, it will be folded back to your baseband signal. Where is the baseband signal? Your baseband signal is up to half. So this part, let me draw that. This part is the alias signal of your original signal. So in practice, we have given the example. You have started with 1 hertz and you have sampled it with a sampling frequency of 2/3. It would be 2/3 or 2/3, and eventually you found that your analog frequency, you get back to your original analog frequency and you found that that is 1/3 hertz. That means this is not your original signal. That is the alias signal of your original signal. So that makes an aliasing of the signal. I can give you very simple example here. For a signal like this, if I choose the value of Fs is equals to 100 hertz. So our signal is, let's say this signal, this red one is 100 hertz, and we are choosing the sampling frequency equals to 100 hertz. So then where the samples we are getting, we got the samples like this. So we are getting a sample here, sample here, sample here, because small f is equals to 100 over 100, which means that this is equals to 1. 1 means what? You have 1 samples per cycle. You have 1 sample per cycle, and those are the samples. 1 sample per cycle, 1 sample per cycle, and so on. Now, if you pass it through the digital, the low pass filter, you will get actually a DC value. You will get a DC value. Is that authenticate from our last example? So let me give you the whole example here in the frequency domain, how we can show that in the frequency domain. So okay, so this is the half, this is 1. Okay, we can restrict up to this. So where is the band of the frequency? The band of the frequency, our original sequence is 0 to 100. So the highest frequency is converted as 1. If that is 99, of course that is less than 1. If that is 98, that is more or less than 1. If that is 0, of course this will start with 0. So we can say that, of course, the spectrum starts with 0 and it will prolong up to 1. In this space, that means in the value of at the value of 1, if I ask you what is the value of the original frequency? In place of 1, small f1, what is the actual value of the analog frequency? What is the actual value of the analog frequency for this case? Any of you? Where we are using Fs is equals to 100 hertz. Can you tell me at the location of f is equals to 1, what is the value of actual frequency? Of course, this is 100 hertz, isn't it? Because f is equals to what? F divided by Fs, and we are looking for f, and Fs is equals to 100 hertz. So of course the f is also 100 hertz. So at this location, f is actually, it is 100 hertz. However, due to the aliasing effect, because it looks like after passing it to the low pass filter, it looks like a DC value. Where is the DC value? This is the DC value. That means this point will be folded to this point. This is a practical example. So of course it will be folded to this point. Similarly, if you draw that, if you have, okay, let me target this point, which is what would be the value? In between half and 1.
So 0.75, sir.
Okay, 0.75. Okay, 0.75. If that is 0.75, can you tell me what is the actual analog frequency at that moment? What is the actual analog frequency? Because you know the value of a small f and you know the sampling frequency. So can you find what is the actual frequency over there? Of course, that is 75 hertz, isn't it? Is that clear to you?
Yes,
Is that
sir.
okay?
Yes, sir.
Okay, so you have what? You have 75 hertz actually. But since that is out of your range, it will be folded back. Where it will be folded back? How can you find that? So how this value will be folded? So in the previous example, I have shown that, okay, if that is 1, practically I can show that, okay, it will be converted as a DC value. But now, if that is 0.75, what would be the value? Okay, that is the question. What would be the value? Now I will explain it with some mathematical terms so that we can understand the process. Okay, in side by side. Okay, I have the signal xn is equals to a cos, this is omega 0 n plus theta. Okay. You can also definitely, the omega is equals to always twice pi f. Okay, we already know this. Now, if there is another signal xn prime, let's say that is a cos omega 0 plus twice pi into n plus theta. What I have done, I have increased the relative frequency by twice pi. I have increased the relative frequency by twice pi. That actually I have done. So if I elaborate this equation, I have found it very easily that is omega 0. Let me write it like this. First twice pi n plus omega 0 n plus theta. So as you can understand that the cos twice pi n, if n is a number like 1, 2, 3, 4 integer value, then it actually doesn't make any sense. So it rotates 360 degree and it actually gives the same value. So it doesn't mean any value for cos or sine. So we can write it very easily that cos, it means that this is cos omega 0 n plus theta, which is nothing but this xn. So try to understand here. We have started with x prime n, which is a frequency omega 0 plus twice pi, but ultimately it looks like xn, which is omega 0 n plus theta. Which frequency is higher? Which frequency is higher? Definitely x prime n is higher frequency, because that is omega 0 plus twice pi, comparing it to omega 0 n plus pi. So it is an example. If I have a low pass filter, and if I give the input as x prime n, put x prime n, okay, then what would be the output? I have got the output as xn, because it actually suppresses some frequency component and it gives the low frequency. And it also shown that in this case, that means in this equation, this kind of higher frequency and this kind of low frequency, they are alike. So that means they are alias. Now for this example, we can also write in this way. What is f0? What is omega 0? What is the relation between omega 0 and omega 0 and f? You can find that value is twice pi f. So if you write it here twice pi f0, I can just replace it. So in that case, we will find it twice pi f0 n plus theta. So the difference is like this. And now if I ask you, what is the distance between this frequency and this frequency? What is the distance between these two frequencies? One frequency is twice pi f0 plus twice pi. That is the frequency. And another frequency is twice pi f0. Isn't it? So what is the distance between these two? What is the distance between these two? In the scale of omega. In the scale of omega, definitely the distance is twice pi. But in the scale of small f, what is the distance between these two? In that case, what you need to do? We need to divide it by twice pi. So if you divide it by twice pi, this equation, you'll find f0 plus 1. And if you divide this equation with twice pi, you can only find f0. So in various way, we can show that this frequency, let me choose the color. This frequency and this frequency have a distance between them. In the omega scale is twice pi, and in the small f scale is 1. So the distance between these two component, this component and this component, has a distance of 1. Try to remember this, 1 in the scale of f, in the scale of small f. So that is the distance. If that is the distance, then they are identical. Now, if I ask you that if this is at the location of 0.75, where you will get the identical signal again. If this is your x prime n, higher frequency component, then where is the low frequency component? Where is that? Of course, before 1. So then we can write it like 0.75 before 1 minus 1. What is the value? That is 0.25. 0.25. Of course, there is a minus. Where is that location? Of course, if this is half minus half, this is that location, 0.25. Okay, let me clear it up. Minus 0.25. This is that location where it should shift. So this value will be shifted here. This value will be shifted here. Are you agree with me?
Yes, sir.
Okay. So then it will be shifted a minus 0.25. As we can understand this negative frequency is just for the mathematical representation that must have the replica at the location of plus 25, plus 0.25. So of course, this black 25 again shifted with a plus 0.25 location. So it will be shifted there. Okay. Another example I can give, if there is a line over this where it will be shifted before one. Okay, whatever the location. Okay, just in general, I'm writing here. Okay, this is the location. It will be shifted. Again, since it is like, let's say minus 4 or something like this, minus 0.4. It is, let's say this is whatever the value. Let's take any value. This is half. So this is 0.6. If that is 0.6, then 0.6 minus 1, which is 0.4. Okay, this is 0.4 minus, of course. So this is a minus 0.4, and minus 0.4 will be shifted where? Minus 0.4 will be shifted where? It is exactly at the location of plus 0.4. So if I make it clear for the whole example, this is half, this is 1. And if you have this kind of scenario, what you are getting, for this example, you have this here. Let's say this is 0.4, or sorry, 0.6, more than 0.5. So it will be shifted where? 0.6 minus 1, that is minus 0.4. Where is that? Let's say this is minus half. So that is 0.4 is here. So it will be shifted here, minus 0.4. And minus 0.4 is exactly equals to plus 0.4. So this is 0.4. So you can find that ultimately 0.6 is shifted at 0.4 location. 1 is shifted where? Could you please help me? 1 is shifted which location? 1 is
0,
shifted which location? Yes?
0, sir.
0.
0.
Because we have shown it. First of all, we have shown it graphically. That means we have this, and if those samples are at this location, this location, it looks like a DC value. That is our first case. So we have already shown that this will be shifted to DC value. And we have also shown that if the frequency in the omega scale, the distance is twice pi, they are identical. Similarly, in the scale of f, if the distance is 1, they are identical. What does it mean? The omega is equals to omega 0 plus twice pi. So that means omega 0 and omega looks like the same. Though omega is a higher frequency and omega 0 is lower frequency, but they looks like the same due to the low pass filter. Okay. Similarly, if you have f is equals to f0 plus 1, you can write even plus minus. Okay, so for simplicity plus 1, they are looks the same. So these two statement, this is 1 and this is 2, they are the same. They are the same statements. Okay. So now it will be very easy task that, okay, from 0.6, it will be shifted to minus 0.4, and then it is shifted to plus 0.4. So of course, if you just repeat this process, you can find that this will actually give you this kind of scenario. This will be folded back like this. This will be folded back like this. Folded back means what? Again, if I want to clarify this, what is the actual frequency? You know that frequency. That frequency actually looks like the DC value. The higher frequency, the lower frequency like this, it will looks like it will be folded back to this place. The other frequency that folded back this place. So similarly, they will be folded back. So now we have all the aliasing signals. So this actually gives the aliasing part of the signal. So you have the full band will be aliased with your DC signal. It means that we have started with 0 to 100 hertz signal. You have 0 hertz, 1 hertz, 2 hertz, up to 100 hertz. You sample it with 100 hertz. Then you have found that, okay, this 0 hertz looks like 0 hertz, and of course it actually stays here at the 0 location. Let's say 1 hertz divided by 100 hertz, it actually stays like there, no problem. I can use the black lines. Okay, so no problem, no problem. You are going through, no problem, no problem, no problem, and up to which you don't have any problem. Can you tell me? From 0, 1, up to which frequency you don't have the problem for this FS? I'm waiting for your response. 0 hertz.
So 50 hertz.
Yes, of course. For 50 hertz, up to 50 hertz, you are going there. So at the location of half, what is the actual frequency? The actual frequency is 50 hertz. What is the sampling frequency? All through this system, it is actually 100 hertz. Okay, fine. Up to 50 hertz, there is no problem. Fine. Now, what about 51 hertz? Do you have any problem? Do you have any problem for 51 hertz? Yes. Can you tell me what is the problem?
So it becomes 49 hertz.
Yes. Then what is the problem? Yes, of course. Thank you for your answer. It 51 hertz becomes 49 hertz. From the diagram, you can understand. Now, what is the problem then? Practically, what is the problem then? Number one, you can't retrieve back your 51 hertz anywhere. So you will actually lost your 51 hertz, because 51 hertz already converted to 49 hertz. So that is the first problem. So you lost 51. Similarly, you lost 52, 53, 54, 55. Have you got the point? Are you convinced with that? You lost all the frequency more than 50 hertz. Okay, all the frequency components. Is there any other problem? Is there any other problem? Yes, there is another problem. For this one, let's say you have 51 hertz, it's converted to the 49 hertz. Do you have the 49 hertz frequency already in your spectrum? Do you have 49 before? I need the response. Do you have
Yes, sir.
49?
Yes, sir. Yes.
You already have 49. Let me draw a diagram that will give you the clear message. Let's say you already have this 49. Let's just think that this is your 49 hertz. Original 49. Though I'm writing the analog signal, it is of course a discrete one. Just think about this. Okay, you have the discrete one. So you have, what is the frequency? This is 49. What is the amplitude of that? Original 49. Original 49. Okay, this is the amplitude. Now you are getting a new 49 hertz. From where? From 51 hertz. You are getting a new 49 hertz from a 51 hertz. This is actually LES signal, of course, isn't it? This is an LES signal from the 51. And this new 49 hertz, you never know that. Let's say the amplitude of new 49 is lower than the previous one. Okay, just to make you understand that this new 49 maybe looks like this. Since the amplitude is low, I'm assuming that will be definitely superimposed. And now how the final 49 looks like. The final 49, definitely they will be added together. And this is the final 49 looks like. Are you agree with me? Are you agree with me? Is this the final 49 hertz?
Yes, sir.
Yes, sir.
Are you happy with this 49 hertz?
No, sir.
No, because it is not your actual signal. Yes, you can preserve the frequency from 0 to 50 hertz. Okay, you can retrieve back, though they are not the original one. They are superimposed by the LES signal. And that is why in case of aliasing, you are not only losing your higher frequency signals, you are also losing the amplitude components or amplitude behavior of the lower frequency component as well. And that is the problem of the aliasing. If I elaborate this scenario a little bit for your understanding, let's say this is half, this is 1, and the scenario is like this. Okay, it prolonged to like this. Of course, from our past experience, we can tell that it will be folded back. Let's say this is 0.75, so it will be folded back up to this. That means 0.25. If you don't agree with me, just raise your voice. Okay. Now you can see that, this is 0. I can put some boundaries here. From this point, from 0 to half, or 0 to 0.25, from 0 to 0.25, you can retrieve actually all the frequencies, all the frequency values. For the last case, you can retrieve, if this is the case. So from 0 to 0.25 for this example, from 0 to 0.25, you can retrieve back all the original frequency. How do you find the original frequency? It's very simple. You need the value of fs, and if you have the value of small f, you can find what is the original frequency. You can get back your original frequency. From 0.25 to 0.5, you can retrieve the original frequency but it is not the original one, actual one. You can get the original frequency, but the amplitude value have been changed. That is the problem. And from 0.5 to 0.75, you have lost your frequency. You have lost your higher frequency. So that is the explanation you can find. And of course, whenever we have that band for 0.0 to half, it is always we have 0 to minus half. Always we can show it like this, because whatever you have in the plus side, you also have it in the minus side. Why is that? This is actually from the Euler's identity, and it is mathematically you can show that, okay, whenever you have positive frequency, you have the negative frequency component. Whether it is not the actual frequency, this is actually movement in the Cartesian plane, rotating clockwise or anti-clockwise. I'm asking to the class if you have any problem to understand this part, because this is very important in practical senses. Okay, we may tell many times, okay, aliasing, this is the effect, aliasing, but we need to understand the effect practically, and that was my objective at the beginning of the class, so that you can understand it properly. Have you understand this fact? Do you have any question, any confusion? If you have, please ask me. Is it
Sir,
fine?
Sir, I have one question, sir.
Yeah, sure.
How we choose the amplitude or the peak? We choose the peak.
In which case you need the peak? Are you talking about the analog signal?
No, sir. This this is the example we.
This example here, the peak means which one? If you can.
Like we choose the decrease from a point.
Okay, you are talking about this line, isn't it?
Yes, yes, yes.
Okay, this is just the hypothetical. Conventionally, when you have some signal like this, okay, let's say this is a ECG signal. In case of ECG signal, if you want to draw the power spectrum, where we have the frequency in the x-axis, omega, and the power, that means the strength in the y-axis, x omega, we have found that the signal component looks like this. Mostly the DC value have higher value. DC component has a higher strength than the higher frequency component. This is a convention. This is a convention, nothing else. Okay, so this is a convention. We are putting this higher value. So if any of you just draw it like this, okay, okay, how can I show you? Like if someone said that, okay, this is my case from 0 to half, this is okay, no problem, because I do not know whenever you are getting this signal xn, what kind of signal is that? It might have the content, DC content has a low strength than the higher content, no problem. But for visual perception, always we are using this kind of concept, and letting that we have higher energy and the DC value, and the lower energy in the higher frequency. That is the concept. Is that okay, Rahman?
Yes, sir.
Okay, so that is a convention, just a convention, nothing else. Okay, any other question? Okay, let me ask you one thing. Have you ever observed any aliasing in your practical life? Have you ever observed any aliasing in your practical life? In any case, have you ever seen that something is rotating? Somehow you know that it should rotate in clockwise. When it is rotating in a small, with a small speed, you can find that, okay, this, let's say this is a stick, you have stapled it, and now you are rotating this. So when it is starting to rotate, you can find that, okay, you can follow that it is rotating in the clockwise. But in some moment, you have feel that it is rotating anti-clockwise. Have you ever seen this? Who ever seen that? Could you please raise your hand? Have you ever seen this kind of effect? Yes, I found one only to see this kind of effect. Disan, are you there? Walaikum salam. Disan, have you seen this kind of effect? Somewhere?
Could not remember, sir.
Okay. Yeah, okay, no problem. So, Aldi, have you seen this?
Yes, sir.
Yes. Okay. Yes. Thank you for your response, Rahman and Hasib. Okay, you can find this kind of thing. What is the phenomena of that one? As you can understand that, okay, let's say you have a camera. You have the camera and you can get the pictures. Let's say what is the resolution of the camera? Let's say the resolution of the camera is 10 per second. This is 10 per second. So in 10 samples, you can collect 10 samples in a second. So whenever, try to understand this, whenever this stick is rotating, let's say it start rotating, at the beginning, it actually take a snap. So how it looks like, so I'm drawing this, okay, collaborating to this one. So this is our original, and this is the picture what we have seen by the camera image. Camera image means that is a video. So okay, I want to video this motion of this stick. So at the very beginning, it will capture this. Okay, I will get this. Whenever it is rotating to this point, then within this time period, within this, so how long it will take? Let's say it takes 1 divided by 10 seconds. So that means let's say make it more simple, 1 per second. In 1 second, it actually take an image. The camera within a second, it actually take an image. Okay, so from this point number 1 to point number 2, it moves and it takes 1 second, and it takes the second image and it looks like this. Okay, fine, we are happy with that. So after 1 second, it will be there and it will goes like there and it will be like this. So if I ask you now, how actually the video camera gives you the perception? The video camera actually gives the perception that it is like a stick, like straight line. It looks like that. I believe you understand. So at the moment 0 second, it takes an image. At the point of 1 second, it will take an image, because in between, when the stick is there, you can't take the image because the resolution is 1 sample per second. When the stick is there, you can't take the image. When the stick is in between, you are not getting the image. So that's why you actually lost the thing. Okay, you are getting lost the image. Okay, now the scenario could be little bit different. What might happen that you are speeding up your rotation a little bit. You are speeding up your rotation. So this is at 0 second. At 1 second, whenever it is at 1 second, within 1 second, this will rotate first there. So this is original shifting. This is original shifting. After 1 second, this will be there. Try to understand. after 1 second, this is at 0 second, and this is at 1 second. After 1 second, this is exactly here. So in this case, what will happen at 0 second? How it looks like? Okay, it was there. Practically, it was there, and you have found that image. At 1 second, where it will be? It looks like it will be there, isn't it? You got my point? So this is at position 1. This is at position 2. This is position 1. This is position 2. After 1 second, according to the rotational speed, this will be at this location. From there to there, how much it will elapse? It will elapse 1 second, and in the third case, it will be there. So at the third case, it will be there. So what your eyes will see by this video camera, it looks like it is there, it is there, it is there. So it looks like it is proceeding to the anti-clockwise direction, though practically it is rotating in the clockwise direction. So this is due to lower sampling rate of the camera. So camera is taking the image 1 sample per second. If you can improve, it is 10 sample per second, you can find that the video will show that it is rotating like this. It is rotating in the clockwise, the original direction. It will follow the original direction like this. So this is called the practical aliasing. So physically, there are some aliasing by sound. There are some aliasing by visual impact. So not necessarily whatever you have seen in your practical life, that is always true. That can be an alias. So the alias is very dangerous because it actually lost the original signal, as well as it actually kill your other signal as well. So that is a problem. So that's why you need to understand how to minimize the alias signal. Okay. So have you got this example clear? The last example. This kind of question maybe, yeah, yes.
Yes, sir.
Okay. This kind of question may be asked in the Viva or in your midterm. So those are important. So these are the physical behavior of the alias signal. Okay, I believe that is enough for today. In the next class, we'll start with the Fourier transform, inshallah. We'll move to the discrete Fourier transform. Before that, I'll talk about the basic or fundamental of the Fourier transform from the continuous and the discrete domain as well. Okay, so thank you very much for your presence.